So today we're going to talk about our last topic in Chapter 5. We're finally almost done with Chapter 5.
Oh, cool.
At least it's still not.
So Monday we will be reviewing, and Tuesday we will be testing on Chapter 5.
Thank goodness I don't have 2 AP tests on the same day. 'Cause we
And
had a
our
test
goal
on
is to be able to solve a word problem today with rates involved. Optimization, we just wanted to optimize an actual value. What if we wanted to figure out speed or things like that? So an optimum speed, or how a speed is working when something else is going on with an expression. So one good example is like when you blow up a balloon. Not manually with your own lungs, but like with a helium thing. It blows up using a particular rate. We could actually track that rate because it's a consistent rate, and we could use that to form an equation about how big is the radius changing, how much is the radius changing while the air going in is changing. So it's more about rates than it is about actual values we're trying to find. So when we're solving related rates, they're a little bit different from optimization. First of all, you should always identify what is given and what you're trying to find when you're solving a related rate. Always. Because the AP graders usually give 1 point just for that. If it's on a free response, if you just identify dV dt equals 700 meters cubed per second. Identifying that along with, possibly you have some other ones, all of those identifications together would be for 1 point. And 1 point can mean a lot when you're taking the AP test. So just like with optimization, if we can, we should draw a picture and then definitely label the picture. So again, this one it's super important on the AB test. It's not as important on the BC test. But you'll probably see at least one multiple choice and possibly a free response that has something to do with related rates. So it's not a super big topic, but details get us facts. So after we draw a picture and label, we can write an equation relating what you are trying to find with what you know. Just like with optimization, that part is very similar to optimization. When we're trying to write our equation, we need to know what we're looking for, know what we have, and somehow relate those together. It can be any sort of geometric. Maybe it's a cylinder or a sphere or some sort of area or perimeter. They usually do geometric ones. It doesn't have to be, though. You can do a trigonometric one. They use those quite often. Pythagorean theorem ones, those are used quite often. And it doesn't necessarily have to be those things. Those are just the more common related rates you see. So the number 4 is also important. This one is different from optimization. We have to identify what is changing over time. I should have probably said over time. And what is remaining static over time. That's very important that we can identify that. Because what is changing, we cannot plug in numerical values. They might give us a numerical value, which we will use later on, but we can't plug in numerical values for changing, while we can plug in numerical values for static. So, oh, sorry. That should have been 5. I rearranged some of the order I wrote stuff in. A good example is like a ladder leaning up against a house. So you have a ladder that starts sliding down. The height that the ladder is against the wall is changing. The base, so So how far the ladder away is from the wall, the base is changing. But what about the ladder itself? Is the ladder changing? It's static. It doesn't change size over time. So that's kind of an example of what it means to be different for changing and static. The ladder is still part of the problem, but it will never change its value. Our ladder is not getting bigger or smaller. So this should have actually said 5. Differentiate implicitly. I didn't rewrite all my numbers. Differentiate implicitly. Then we can substitute in all remaining values, and then we solve with units. Usually we're trying to look for one specific thing, so if we substitute in our values, then we can go and solve for h or r or dv dt or dA dt. Usually we're looking for one variable, and we're actually looking for a numerical value with that variable. So I want to make sure everyone has this written down before I go down to the example. So let's assume the radius r of a sphere is a differentiable function of t, and that v be the volume of the sphere. Find an equation that relates dv dt and dr dt. So this isn't a full-scale related rates problem. It's just to help us with the beginning setup of how do we find these equations. This one we're going to stop just after we find the equation we would use. So this one we're not going to follow the steps that we have written down. We're just going to worry about writing out the equation right now. So first we need an equation. We can't get dv dt or dr dt unless we have a volume and a radius. So first we just need a regular equation before we implicitly differentiate that to get those values. So what equation do you think we would use? It gives us a pretty good hint as to what equation we would be talking about geometrically. Volume of a sphere. Do you guys remember the volume of a sphere? Nope. No. It does involve r cubed though. Okay, so this is something again that we should start becoming familiar with, is some of our geometric formulas we haven't seen for a while. Volume of a sphere is 4/3 pi r cubed. Hopefully I'm remembering that correctly. I'm pretty sure. That is volume of a sphere. So we want an equation that relates dv dt and dr dt. So we will be implicitly differentiating, but this time we're implicitly differentiating with respect to time. We're trying to differentiate with respect to time. When we did, I think the warm-up problem was this equals 2x. How did we differentiate y? 1 times y prime plus x differentiated normally. But let's do this in Leibniz notation. What if I did this same problem in Leibniz notation? derivative of y is 1, and in Leibniz notation, what would we multiply it by? That's what we... Yeah. dy dx.
Okay.
The top number, or top letter variable is what we're trying to take the derivative of. The bottom is what we're trying to take the derivative with respect to. So dy dx. What about the derivative of x? 1. How would I write in Leibniz notation what would come next? If this was the derivative of y with respect to x,
dx, dx.
this is the derivative of x with respect to x. Which is why we don't write it out. What's going to happen with dx over dx? 1. So same thing over here, 2 dx dx. So now when we differentiate with respect to time, we're not going to have these things cancel out. None of this equation is time. We have volume, we have radius. When we differentiate with respect to time, we can't cancel out if we have radius over time or volume over time. So we take the derivative, though, the exact same way we did with those things. How do I take the derivative of a variable v? Okay, but we've got to use Leibniz notation now. This is where it's really, okay? So derivative of v is 1 times dv dt. The derivative of volume with respect to time. The volume is changing over time. This is all about a rate. We have a volume that is changing. So again, this one's more like a balloon. If we filled up a balloon, let's say my balloon is like this. Right now I have a pretty small volume. Over time it gets bigger. Now I have a bigger volume, even bigger. My volume is changing over time. So is my radius. Right now I have a small radius. As I get bigger, I get a bigger radius. We're actually changing these values over time, which is, I mean, being able to do stuff like this is very useful for the real world, like if you're an engineer. Most things move when you're engineering. So you need to be able to figure out and compare rates of things. So now we go to the other side. How would I take the derivative of this? Not worrying about the Leibniz part, just the derivative of this. Power rule. So using power rule, what would we get? 12 thirds, which is 4. So 4 pi r squared, because 4 thirds times 3 is 4. Now I have to worry about my derivative notation. What would this multiply by? If this
dr
is
dt.
dv dt, this is dr dt. The variable we're working with over time. So this would be our related rates equation. And we could do stuff to solve with it, but right now we're just worrying about what is this related rates equation. So I'm going to have you guys try one really quick where you're just worrying about how do I find this related rates equation. Also keep in mind if you have multiple variables and they're interacting with each other, they still follow the laws of differentiation. If we have 2 variables multiplying, we still have to use product rule. 2 variables dividing, we still have to use quotient rule. I'm going to pause the recording for a second while you guys work on the try problem.
Put it over 3.
So you should have gotten this as your answer. Maybe in a different, you could simplify a few things, like I don't really have to write times 1. You should have gotten that as your answer.
This is
Now-
so many words and it's
Yes.
confusing.
These are very large word problems. I could also hold stuff constant. I could tell you to treat this letter as a constant. That is possible. So let's take this same equation.
Okay.
Let's say I have a cone where the height is never going to change. It's always a certain height, but the radius can change. Okay? So what if I tell you specifically height is constant? I used the word static in the instructions, constant. Static because that means not changing. Not static as in like noise. Okay, so if I told you to treat h as a constant, the left side's still the same. Derivative of v is dv dt. What about the right side? If h is constant, how am I going to take the derivative of this now? Treat it as a number. If we have this number timesing by this, what do we do with numbers times by a variable when we're taking the derivative? What did we do with 1/3 when we were taking the derivative? Well, we had to do power rule because our variable is a power, but what happened to the 1/3 when we used the power rule? I mean, it multiplied by the 2, but it didn't.
Just stays there.
It stayed there and multiplied by the 2. Thank you, Jason. So h is going to do the same thing if we're treating it as a constant. So if I take the derivative of this, I'd still bring 2 out front. 2 times all this stuff. And then I still times by dr dt. Again, I wrote it a little bit differently just to show that a lot of the stuff didn't change. Usually we would just automatically do the multiplication and get 2/3 pi hr or rh, it doesn't matter. So if I tell you to keep it constant, we don't have to differentiate it with respect to time. Or if the instructions tell you to keep it constant. That is a possibility, is to keep something constant when you're working. That's a good example. That's a good real life example. One they do quite often is a shadow question. So let's say there's a lamp post over there and it's dark.
Oh,
So if I'm standing here, which way is my shadow facing?
this way.
This way. Okay. So I am forming a right triangle if we consider the distance from the top of my head to the tip of my shadow. So as I walk, what's changing and what would we not differentiate? If we're, okay. The shadow is either getting shorter or longer. So what else is changing? We have 3 distances. We have me.
You're getting
My
further away from the
shadow.
lap post.
I am getting further away from the lamppost, so that's a
distance
distance
from your
that's
head to the
changing.
tip of the shadows changing.
Head from the tip of the shadow is changing. What is not changing?
You.
My height is staying the same.
Unless you're getting high heels. and
So-
you're walking up a ramp.
Let's
The
assume it's a
lamppost
flat
height isn't
surface. The
changing.
lamppost height isn't changing. So if we were given an actual problem like that where we're then applying it, we would consider me, the person, a constant instead of a variable, and we wouldn't actually differentiate that piece. Usually though, when we're doing real life examples, what we would do instead is plug in a value. Like for me, we'd plug in 5.5. We're converting to decimals. I'm 5'6", so 5.5 feet. Yeah. So we would plug that one in, whereas everything else we would leave in variable form because it's changing. So let's do one last example.
Holy cow. Once upon a time.
I know, I feel like we're writing a novel today, I'm sorry.
You pause the video.
I unpaused it, I believe. And I quote, "The red light is blinking." So we have a hot air balloon rising straight up from a level field, is trapped by a rangefinder 500 feet from the lift-off point. At the moment, the rangefinder's elevation is pi over 4. Sorry, I was too lazy to type that in with the pi symbol. I have to go plug it in as an equation. But just write in the pi symbol. The angle is increasing at a rate of 0.14 radians per minute. How fast is the balloon rising at that moment?
Pi divided by 4.
Yes, pi over 4, so. So at this particular problem, I think it would be good to draw a picture and identify what's given at the same time. We need to also label things so we know what to call them when we identify what's given. So we have our hot air balloon. It's very beautiful. We have our field. And the hot air balloon is rising straight up from the field. And then we had a rangefinder 500 feet from the liftoff point. Where would I put the rangefinder on my picture? Over to the left. So rangefinder is like basically a little camera that's tracking. So it's looking and tracking the angle. Where the hot air balloon is at. So I could label a few other things. What else could I label from the information given? Distance. Where would I put 500 feet?
On the base of the tree.
From
Base of the triangle. We might think from the rangefinder to the hot air balloon, which is a possibility, but they specifically said from the liftoff point, not from where the balloon is currently at. So 500 feet from the liftoff point. At the moment, the rangefinder's elevation angle is pi over 4. So at this particular moment in time, this is pi over 4. But will the angle here change? It'll get bigger. So we are not going to label this as pi over 4 right now because it can change. And the angle is increasing at a rate of 0.14 radians per minute. So this angle that's moving at this particular moment in time, it's actually moving at 0.14 radians per minute. So looking at this, how could I label 0.14 radians per minute? If this is a rate, how do we label a rate? What do we mean by rates? Instantaneous rates. Derivatives, okay? What notation for derivatives are we using right now?
What's his faces?
Leibniz's notation. So usually we would do dy dx, but we need to keep it in reference to our problem. So what are we going to label this? Close. It is going to be over dt. What's changing over time that we have this rate for? The angle. So d theta dt was 0.14 rads per minute. We should also label units with this. So what is it asking us to find? It says, how fast is the balloon rising at that moment? So it's asking for a speed, a velocity of what part of this picture?
Side.
The balloon. So this piece right here is changing over time. So we need to give it a name. What should we give this a name as? B, okay. So we are looking for dB dt. That's our goal, find dB dt. So we need an equation relating the angle to B somehow. What equation could I use that would relate these two things together? A trig equation on this one. What trig equation specifically?
Tangent.
Tangent. So we'd have tangent theta equals opposite over hypotenuse. So we have an equation now. Let's take the derivative of our equation. What's the derivative of tangent?
Secant squared.
Secant squared. But when I take the derivative, what do I have to multiply by?
D theta dt.
D theta dt. What about the other side? B over 500. Except that 500 is on the bottom. So what if I rewrote this as 1 over 500 B? The
No,
constant
just
would just be 1 over 500 times dB dt.
I didn't forget you product rule. I was wrong, but I didn't forget.
But you didn't forget it. So now that I have this equation, I could actually plug in my values and solve for dB dt. We knew theta at that particular moment in time was pi over 4. D theta dt was 0.14. And we could then go solve for dB dt, which is just algebra at this point, and we're running out of time. So we're going to skip that part. I think we're going to take 2 days on this and not just one. So Monday we'll actually do one more day of related rates, Tuesday review, Wednesday test. And that particular test will go on quarter 2 since it's so close
Why do you
to
have
the end of it.
You can't square.
0.14.
Oh,
There's
is
a
that
decimal
times?
place.
Times 0.14?
Yeah, times 0.14.
Oh, my.
Yeah.
Okay.